Greetings, this is Professor Roman. Let's continue the lecture series on linear algebra. Today I have a short lecture for you finishing chapter 8 of the book. And that leaves us with chapter 9, which is canonical forms. We're going to talk about something that you very seldom see in linear algebra books. We have seen already that two real square matrices are similar over the complex field if and only if they're similar over the real field. That was a theorem we had in chapter 2, 2.76. The same result holds true for unitary similarity, although this fact is not as well known as maybe it should be. And that may be because the proof, at least the proof I've seen, is somewhat unintuitive. So I'm going to try to lead you through the proof by reasoning out the steps. By doing essentially what mathematicians do, and that is they gather their facts and they ask a series of questions. But despite my meager efforts, this proof and the proof of theorem 9.12 in the next chapter are probably the most difficult proofs in the book. One of the features to note of the proof I'm about to give you is how it depends on a solid grasp of earlier theorems. In particular, two theorems from the previous earlier in this chapter. It's a fine example of how the mathematical disciplines build on themselves. You can't study some theorems and then forget them and expect to be able to continue your studies. You've got to remember the theorems. They're your tools that you work with in proving other results. So here's the theorem. Two real matrices A and B are unitarily similar over the complex field if and only if they are orthogonally similar over the real field. So we know that there's a unitary matrix U for which UB equals AU, or put another way, B equals U star AU. And we want to show there's a real orthogonal matrix O that has this same property. And somehow we have to take advantage of the fact that A and B are real matrices. So for convenience, let's refer to this property that U has here as the swapping property of U, just to give it a name, a handle, so I can talk about it. I wouldn't suggest using it outside the context of this proof. So what we need is a real orthogonal matrix that has the swapping property. Well, we might begin by asking ourselves, what other matrices can we find that have the swapping property? And some measure of thought might make you come to the answer that if you have a matrix that commutes with A, then NUB will be NAU because U has the swapping property, and if N and A commute, you'll have ANU, and so NU has the swapping property. Any matrix N that commutes with A, you can multiply by U, and you'll get another matrix that has the swapping property. So all we need to do is find a matrix N that commutes with A and for which NU is real orthogonal. That's actually not such a trivial thing, but that's where we are now in the proof. And at this point, it's wise to gather our facts together so we can stare at them in one place. First, we have the original equation, UB equals AU. By assumption, A and B are real, so they're equal to their own complex conjugates. The unitariness of U can be written in a bunch of different ways. U inverse equals U bar transpose, U bar equals U transpose inverse, U transpose equals U bar inverse. They all say the same as U star equals U inverse. And at this point, we don't know whether any of those are going to be useful, but it's good to have them written down so that if something pops up, we can look at these formulas and say, aha, there's a match. Now we do some exploring. Starting with the original UB equals AU, we'll take complex conjugates. U bar, and this is B bar, but that's equal to B, so we're using the realness of B, equals AU bar. Well, so U bar has the swapping property. If we replace B by U star AU, or in other words, U inverse AU, in here, we get U bar U inverse AU equals AU bar. This is just fiddling. We don't know at this point whether it's headed anywhere or not. I suppose you can guess that it is because I'm going through it, but oftentimes we just write down equations and we fiddle with them hoping something will work out. Don't like the complex conjugates, hard to work with. But one of the formulas they gave earlier says that U bar is U transpose inverse, so we can stick that in. This is a mess, definitely begs to be cleaned up. So here's some algebra, here's some more algebra. Where are we now? We have found a matrix, UU transpose, which I'll call N, that commutes with A. Well, that's some progress. Unfortunately, NU is not, in general, orthogonal. NU transpose looks like this, NU inverse looks like this. They don't look like they're going to match. Maybe by accident, but in general, don't look enough the same to expect them to be equal. But at least we can say that we have this matrix N equals UU transpose that is unitary because U is unitary, and it is complex symmetric. If you take the transpose of N, you get N back again. So maybe that'll be helpful. Now we remember theorem 853, which tells us since A commutes with our N here, UU transpose, A also commutes with any function of UU transpose, because these functions are just polynomials in UU transpose. So A, f of UU transpose equals f of UU transpose A. So we've got more matrices that commute with A. Maybe we can choose a function that will help us here. So we'll just, for convenience, we'll set f of UU transpose equal to m. So we have MA equals AM. And all that remains, however difficult it might be, is to choose a function f that makes MU, which is this quantity, real orthogonal. Well, the orthogonality condition for MU is that its transpose is equal to its inverse. And we'd like to solve this for M, and if we're lucky, we'll get something we'll get an M for which MU it will be orthogonal, because that's this condition, but it will also be real. So how do we solve this for m? Well, of course, first we'll distribute the transpose and the inverse, and then move the m's to one side. And I've taken inverses of both sides here. And this is m inverse m star equals UU transpose. It looks like we might be stuck. Unless we realize that if we could pick a function f for which m is unitary, then m star is m inverse. We get m to the negative 2 equals UU transpose. And so we could take m to be the square root of UU transpose inverse. So this is f now. F of z is the square root of z inverse. We need m to be, back up here, we'd like m to be unitary. Well, it is unitary, because we know that UU transpose is unitary, and f takes the unit circle to itself, which means it maps the eigenvalues of UU transpose, which are on the unit circle, to other eigenvalues that are on the unit circle. So the image is a unitary map. So m is unitary. I don't know if you'd say we lucked out or not. Maybe so. Okay. Not only is m unitary, but mu satisfies the orthogonality condition, because that's where we got m from. And mu is real because it's both orthogonal and unitary. And that means its transpose is equal to its inverse, and its conjugate transpose is equal to its inverse, so it's equal to its own conjugate, complex conjugate. So we found the matrix M commutes with A, and this is real orthogonal, and we are done.